The vast size of our universe and the fact that light has a speed limit, a special speed at which it can travel, means that every time we look at a very distant object, we're actually looking at that object in the past because it takes light so long to leave from that object to get to us. Now, the speed at which light can travel, we know to be 3 × 10⁸ meters per second. Nothing can travel faster than the speed of light. So anytime I talk about light or the electromagnetic spectrum, all light travels at the speed of 3 × 10⁸ meters per second. Now, 1 light year is the distance that light can travel in 1 year, and that distance is about 9.5 × 10⁻15 meters. And because our universe is so vast, and because light has a speed at which it can travel and it can't go any faster than that, that means that the further and further back we look in space, the further back we're also looking in time. But we can get a good sense for astronomical distances by considering the time it takes for light to travel that distance. So if we want to calculate the time it takes light to travel some distance, we have to come up with an equation. What equation will we use? Well, let's think about speed. We know that when we drive in our cars, we drive at some speed in miles per hour. A mile is a distance, an hour is a time. So a speed must be a distance over time. And so we find speeds by taking the distance that we travel divided by the time it took us to travel that distance. So if we rearrange this equation, we see that that an equation for time is equal to distance that we travel divided by the speed at which we traveled. So we can calculate how long it takes light to get to us from a distant star or galaxy if we know the distance to that object and we already know the speed of light. So because the distances between individual stars and galaxies is so great, it is unlikely that humans could ever reach a planet beyond our solar system in a human lifetime. That's really disappointing. We'd love to be able to do that unless any of you can figure out how to travel faster than the speed of light. Now, even if we travel at 20% the speed of light, we could get to Proxima Centauri, which is the nearest star to us, in about 20 years. Now, the cool thing about the distances between things is that often we refer to the distances between stars in units of light years. So 1 light year is the distance that light can travel in 1 year. And so if I tell you that a star is 8 light years away from us, it also means that it took light 8 years to leave that star to reach us. So something 8 light years away, when I see it in the night sky, it took light 8 years to get to my eyeballs from that star. So that means I'm actually looking at that star as it was 8 years ago, not necessarily as it is instantaneously right now at this very moment.
We're going to think about an object called the Homunculus Nebula. It is located at a distance away from the Earth of 7.10 times 10 to the 19 meters. Okay, that's really far away. It's called the Homunculus Nebula. Homunculus is Latin for little man, and it looks sort of like an hourglass-shaped nebula explosion of cloud of gas and dust. And it's caused by 2 stars that are spinning very, very rapidly around each other, supermassive stars spinning rapidly around each other, and they're sort of, they interact with each other and they emit this cloud of gas and dust that looks kind of like the shape of an hourglass. So it's located at this distance away from us. We're going to figure out how long it takes for light to get to us from that object. Okay. Calculate the time in seconds that it takes light to travel from the Homunculus Nebula to us here on Earth. So how are we going to find that if all I've been given is the distance that this object is away from us? Well, we know that light travels at a certain speed. Okay. Light travels at the speed of light, which is known to be 3 × 10 to the 8 meters per second in a vacuum, or essentially space. Okay, so we have a speed, we have a distance, we are looking for the time. Now, there's a really useful equation for us in science, in physics, that a velocity or a speed is equal to a distance divided by time. So we know at the speed at which light travels. We know the distance at which the Homunculus Nebula is away from us. Now we just need to solve this equation for time, plug in our values, and we'll get our answer, okay? So what I'm going to do, I need to solve this equation for time. So I'm going to put v over 1. You can always do that here. So now I have v over 1 equals d over t. To solve for t, what I can do is cross multiply. I can multiply v times t and set it equal to, essentially, we've got d times 1, so I'll just say equals d. Then I'm trying to solve for t here, so I can divide both sides by v. So now I have an equation that says time is equal to distance over velocity, which in this case is the speed of light. So the time it takes light to get to us from the Homunculus Nebula will be the distance at which the Homunculus Nebula is away from us, 7.10 times 10 to the 19 meters, divided by the speed at which it travels, that light travels, which is the speed of light, which is 3 times 10 to the 8 meters per second, okay? And then, so what we do is we're going to take our 7.1 times 10 to the 19 and divide it by 3 times 10 to the 8, okay? So this is 7.1 over 3 times 10 to the 19 minus 8. Okay, so what are the units going to be here? Well, we're looking for units of time. We've got a meter divided by a meter per second. So if you think about those units, we have a meter. I'm going to write it as a fraction. We can always write something over 1. So meter over 1 divided by meters per second. It's the same thing. When you divide by a fraction, it's the same thing as multiplying by a reciprocal. So meter divided by 1 times dividing by this fraction, same thing as multiplying by its reciprocal, which is seconds over meters. I see that the meters and meters cancel, so then I'm just left with seconds. So that tells us that meters divided by meters per second gives me a unit of seconds. So this answer is going to be in units per second, which is time. That's what we're looking for. Okay, so now we've got 7.1 divided by 3, which is 2.37 times 10 to the 19 minus 8. We subtracted our powers on our 10 here because we're dividing, and then that gives us 11. Okay, so then we have our answer is 2.37 times 10 to the 11 seconds. Now, what if we wanted to convert that from seconds into years? So let's do that here. 2.37 times 10 to the 11 seconds times, remember we're going from seconds to years. Let's see. There are 60 seconds in 1 minute times 60 minutes in 1 hour. We got to get to years. So times 24 hours in 1 day times 365 for a minute. I forgot how many days there were in a year. Days in 1 year. Okay, so let's check. We've got seconds canceling on top and bottom, minutes cancel, hours cancel, days cancel, and then we're just left with units of years. So we've got 2.37 times 10 to the 11. Don't have to multiply it by anything else other than 1. And we divide it by 60 times 24 times 365. And then that gives us about 7.5 times 10 to the 3 years. Okay, so it takes, and if we write that out in its decimal notation, we've got, or expanded out from not putting it in scientific notation, that it takes 7,500 years for light to travel from the Homunculus Nebula to Earth. So anytime we're looking at a telescope image of our Homunculus Nebula, we're seeing it in that instant as it was actually 7,500 years ago.
So now that we've talked about distances and how long it takes light to travel through our universe, I want to talk about the cosmic timeline of our universe. And if we imagine that the whole timeline of our universe from the Big Bang, the creation of our universe, to now could fit within one calendar year, we see that January 1st, the Big Bang occurs. Our Milky Way galaxy forms in May. Our solar system forms in September of that year. Earth doesn't get an atmosphere that's oxygenated until October. In November, life forms start to appear. And then it isn't until December 19th that vertebrates start to appear. And then we have plants. Dinosaurs appear on the 25th of December, just in time for Christmas. Mammals appear just after that. On December 30th, dinosaurs become extinct. And it isn't until December 31st, the 50th second of 11:59 p.m. that the invention of the alphabet occurs. Our humanity is really just a tiny blip on the radar, the whole scale of our universe. And here are a couple of other photos that I think are really great that sort of bring everything into perspective. We think about living on our planet and how important our life and our world is to us, but really in the grand scheme of things, we're just a tiny pale blue dot. So this photo is called the pale blue dot, and it's a photograph of our Earth taken on February 14th, 1990 by the Voyager 1 space probe from a distance of about 50 AU, 50 astronomical units, 50 times the distance between the sun and the Earth. And so at that distance, we look back into our solar system, and the Earth is nothing but this little dot right here. And here's another photo. This is of the Earth rising above the moon. This is the surface of the moon. And this was taken on December 24th, 1968 by Apollo 8 astronaut William Anders. And so there they are on the surface of the moon. Here we see craters on the surface of the moon. And rather than like on the Earth, the moon rising in the sky, here they're on the moon and they see the Earth rising in the sky. And that was humanity's first photo in 1968, ever stepping back from our Earth and looking at us from afar. And it's really amazing to think that our beautiful Earth is just this little pale blue marble in the whole scheme of our universe.